Hello and welcome back to module number 10. Today we are going to talk about ANOVA and what does it stand for and why is it important. I will also we'll talk about what is it, the ANOVA, how to apply to it. I will give you some background on ANOVA and how to analyze. But of course, I will also highlight or provide example of ANOVA using R. And this is example that was presented in conference in 2015 and everyone liked the idea and it really works fine. So this will give you indication how to conduct ANOVA with R and how to apply to it. I'm sure it will be a little bit confusing at the beginning, but make sure that you understand or ask questions. Okay, so why are we talking about ANOVA and what is the idea behind ANOVA? So the idea behind ANOVA is to determine the difference between the mean. What does it mean, difference? Remember that when we started talking about a sample and we are taking a sample and we are comparing it to the population. So ANOVA help us to diagnose or to find the difference between the sample and the population in order for us to make sure that we are in the right lane to make a conclusion about the sample and how it reflects the population. So the difference, and this is important, the difference between ANOVA and the t-test is that ANOVA is used where there is two or more means being compared. And that is the difference between a t-test, which is limited to only two means. ANOVA allowed us to compare more than two in order for us to analyze. So the idea of ANOVA basically is to protect us with regard to type 1 error. Remember that when we have the type 1 error in hypothesis testing, we are trying to make sure that we are not stepping into the type 1 error when we are comparing two or more population means. In the population, the sample versus the entire population. So again, the logic and the process of the ANOVA is the idea that, again, the t-test is to evaluate all the mean differences, and we are trying to achieve by ANOVA by trying to see more than one or three means in order for us to avoid the type 1 error and to have alpha level to that correspond to the testing for the final experiment of the alpha level not to be quite large. I know that it's big words, and I hope that my example will make sure that it is make more sense. So ANOVA allows researchers to evaluate all the mean differences in a single hypothesis using a single alpha level, and thereby try to keep type 1 error under control. Although ANOVA is used in variety of different research situations, in this chapter, on this module, I use the word chapter, in this module I will present only the independent measurement design, only one dependent variable. I will talk about two-way ANOVA later on, but it will not be in depth. So what are we talking about? We are talking about population. We have a treatment and we have second treatment or third treatment, and we take a sample and we have the idea how can we make sure that we are not stepping into type 1 error in that stage. So the idea or the logic and the process of ANOVA is the idea of using F ratio. F ratio is the idea of two sample variants. In the context of ANOVA, we are calling it the mean square or the MS values. So the top of the F ratio of the MS, or the mean square, measure the size of the mean difference between the sample, and the bottom ratio of the MS measure the difference that would be expected without treatment of the effect. So the issue here is that the F ratio has the same basic structure as the independent measurement of T statistics presented in module number 8. So in this case, the F ratio is equal to obtain mean differences divided by the differences expected by chance, and it is basically the MS between versus the MX divided within. So what are we looking for? We are looking for the differences of the measurements of the difference due to systematic treatment, or measurements the difference due to unsystematic factor. Those are the things that we are looking at. So the logic and the process of the analysis of variance is that the large value of F ratio indicates that obtained from the sample mean difference from an or greater than that would be expected if the treatment has no effect. However, each of the sample variance, the MS value, in the F ratio is computed using the basic formula of simple variance, which means that SS divided by DF. Okay. One thing I need to highlight here before I'm going to go back to what is SS and what is DF. So one way ANOVA is designed to assess the interrelationship of two independent variables onto the dependent variable. In one way, ANOVA is the one factor or the independent variable analyzed has three or more categorical groups, and that's the aim of the ANOVA, one-way ANOVA. In a two-way ANOVA, we are compare multiple groups of two factors. Okay, back to our discussion, back to our definitions. So basic definition of DF, which means the degree of freedom in the source. So since each sample has a degree of freedom equal to 1 less than the sample size, then the K samples, the total degree of freedom is K less than the total sample size. So DF basically is equal to capital N minus K, and the N, capital N, is in this case the sample size. SS means the sum of squares due to the source. So the variation due to the interaction between the sample is denoted by SS, the sum of square between the two groups, and there are K sample involved in one data value for each sample, so that there are K minus 1 degree of freedom. The formula in this case, again, this is a factor one-way analysis of the variance. Again, the factor, the error, and the total. And again, this is where we are coming together in order for us to measure the difference between the total equal to between plus the error in order for us to understand it. So the logic and the process of analysis of variance is to obtain the SS value and the DF value must go through the analysis that separate the total analysis of the entire set of data into two basic components: between treatment and within the treatment. And that's where we are trying to compare that in order for us to validate that. So the two components of the F ratio can be described as between minus treatment, in this case, the treatment of the study. So by comparing the variance and the three means, we can measure the size of the differences, and that's where we're looking for in order for us to verify. Although it is possible to compute the variance for the set of sample means, it is, again, very important, it is usually easier to use the total t for each sample instead of the mean and to compute the variance for the set of t values. So the logical behind that is the difference between the means that can be caused by the source. So the treatment effect that can be added or to be account for, and the idea what it really means, and the chances or the sample error. And this is something that nowadays we are going to see that quite a lot with regard to the election. They will say to us that this candidate is going to win in a sample error and they will give us a percentage. This is how they do that. This is where they will say to us a sample error can happen because they might be no treatment or might be some differences between the sample that they took in order for them to predict who is going to be the next governor or the next representative in the House of Congress. Who knows? But this is the part of the process that we need to be aware of. Within treatment, the measure of the size of the difference that exists inside each of the sample. Because all the individual in the sample receive exactly the same treatment, any differences within a sample cannot be caused by different treatment. And this is important. And thus, those differences are caused by only one source, and that is chances or error. And the idea is that we are trying to define or to be more cautious about the chances and the error that we are going through our process in order for us to verify it. So the consider for the sources in this case with regard to the F ratio is the treatment effect plus the chance divided by error and divided by chance and error. The logical when we are stating the null hypothesis is true and there is no difference between the treatment, the F ratio is balanced. But when the treatment effect is zero, the bottom and the top and the bottom of the F ratio are measured the same variance. In this case, you should expect the F ratio near 1, and when the sample data produced, the F ratio is also near 1. So we conclude there is no significant treatment effect based on our study. And I need to say one more on the other hand. And in this case, a large treatment effect will produce a larger value for the F value. So, and that happens when the sample data produce a very large F ratio. We will reject the null hypothesis and conclude there are significant difference between the treatment. In order for us to determine whether the F ratio is large enough to be significant, you must select the alpha level. And to find the F values and the ratio value, we also have to consult with the F distribution and to find the critical value. So the idea here, and this is my own drawing, I'm sorry it's not clear and crispy, but here is the issue. F is equal to the difference between the treatment and the variance within the treatment. Each variance in the F ratio is computed by SS divided by DF, and it is the variance between the treatment and the variance within the treatment. And we are also looking at the total versus the difference. And in summary, this is what we will see, and we will see that also in R. So in the past, we used to have a table, a print table, in order for us to make all those connections and all those measurements. In this case, we need to know the definition of DF, SS, MS, and F in order for us to understand how the R is conducting ANOVA analysis. So DF is the mean of the degree of freedom in the source. SS is the sum of squared to the source. MS is the mean sum of the squared to the source. And F stands for the F variable. So when we are using a null hypothesis for ANOVA to state that the general population, there are no mean difference among the treatment being compared, and when the null hypothesis is rejected, the conclusion is that there are no significant mean differences. However, and again, this is again sidekick, the ANOVA simply establishes the difference that exists. It does not indicate which treatments are different from each other. And when we have more than 2 treatments, this can create a problem. Specifically, you must follow the ANOVA with additional test called post-test to determine exactly which treatments are different and which one is not. I can give you an example from my own study. I conducted a study with regard to how people react to visualization, and one of the things that the reviewer came back to me and asked me for post-test to determine how my treatments into visualization treat differently from different population. So it's becoming a little bit more complex. My objective is that you will know the mechanics. I want you, in the end of the class, you know how to apply ANOVA into R and to understand what does it mean. So in this case, I need to state what is the additional element of the analysis. Example, post-test is part of requirement, but it's not a requirement to every single field. It is requirement when we are talking about humans. And so again, this is a sidekick. We also can use other type, and we can apply tests done after the ANOVA where the null hypothesis is rejected when there are 2 treatments condition. The test compare the treatments 2 at a time and to test the significance of the mean of the differences. And there is another issue, another hypothesis testing. ANOVA also allowed us to evaluate the significance of the sample mean differences. That is, are the difference bigger than the reasonable to be expected just by chance? And this is another element that I want you to start thinking about. When you have a large sample, is it possible that there is a small mean difference between to be significantly significant? And if it does the hypothesis test does not necessarily provide enough information about the actual size of the mean differences. So the measurement of the effect side is a big issue. I will not go into depth about every aspect because I introduce you to ANOVA. But I want you to keep it in your back on your mind in case you will run into this problem, in case that you will be asked what to determine. So again, I lay out to you the framework that you are measuring the effect side for the ANOVA and how to do that. And usually this is where the effect looks like. So we have example drug treatment and how it been affected, and this is how it land out. Okay, so now to the main subject of our module, and that is how do we apply ANOVA into R. So first of all, we have to have 2 variables, the y and the x. And what it does, it allowed us to identify what type of test, what are we testing, and what are we following here. So in the last line in my PowerPoint presentation slide, you're going to see AVO dot test1 equal AVO, and notes not equal to object is, and I provide summary. So the is the data name for ANOVA. And this is and the summary is the data name for ANOVA, giving that ANOVA is the output. I hope it makes sense. If not, please ask questions. So in this case, this is where I'm testing test Y versus test X, and that's where he will come back to me and provide me with an answer. DF is 2, sum square is 590, and mean square, the p-value, and he will provide me with this information. Your objective to ask what does it all mean. So let's start with the basic. The p-value in this case is the PR smaller than the f. In this case is 0.345 as I calculated over here. And in this case it's greater than 0.05, which is 5%. And as a result, it is significant level. That is why we do not reject the null hypothesis. Again, the null hypothesis with a p-value, we are looking for a smaller value than 0.05 in order to accept or reject the null hypothesis. I'll also provide you with a PDF file that I'm going to go over quickly, and I hope it will make more sense. I'm going to make it full. Hold on a second. Okay, so okay, so in this class we are going to handle V. I gave you 3 examples of 3 variables, Y1, Y2, Y3, and now we are trying to combine them into one longer vector. Remember what a vector is a group, and in this case we are providing it as a vector. We will call it as a group, and we will be able to tap into it in order for us to calculate. So in this case, we are tapping into it. We are trying to establish what is it, the function that we are trying to apply, and the idea of the ANOVA and ANOVA fit and ANOVA misfit, and in order for us to validate, in order for us to do that. In this example, I displayed to you what is data frame. In your class notes, you will see also about what is data frame, how to apply that, and how to define it. And again, look at the example how I play with the DF as ANOVA, and how do I measure that in order for me to come up in the end with a result that will tell me what is the result of it. I'm not going to go inside. I'm not going to analyze every aspect. Maybe I should, but I want your reaction. Say to me, yes, it makes sense. No, it doesn't, and I will explain it more. I want you to read about ANOVA. I will give you more information about ANOVA and ask questions. That's it for now. You're going to have a simple example assignment of ANOVA with R, and I hope it makes more sense. Until next time, enjoy ANOVA.